Thank you for this nice invitation. Today I will speak about how we can do efficient ensemble forecasting by exploiting deep learning, by exploiting generative flow models, and how we can combine these models with data assimilation. This work is a joint work together with Marc, Bocquet, Freddy Bouchet from LMD, and Etienne, Mémin, and others. We want to develop an efficient ensemble forecasting framework, and so to set the scene, the goal is here to have the current conditions, so which can come out of an analysis product, and the goal is to do a prediction for a time window which can be here, for example, 12 hours. And the first part of my presentation will be all about CIs, but the framework that I will present is generally applicable to basically any component of the Earth system. And so the main idea is we want to develop such a framework, and so let's use deep learning for this. Let's use, for example, a convolutional neural network, a transformer, whatever, to do this prediction. And as I said in the title, we want to use generative modeling for this. So generative flow models, and there are already very much, or many examples of this for the atmosphere. So we have, for example, Jenkins from Google DeepMind. Another example is Climate in a Bottle from NVIDIA. So we have really big groups working on these generative flow models, on these generative deep learning models for weather prediction. But still, it is a field that has been developed in the last two to 3 years. And so the general idea of these generative forecasting models is that we have our initial conditions, and we might have also external forcings, which are here kind of important for CIs. And during training, we know what we want to predict. So we know, for example, how the CS looks like in 12 hours. And so what we do during training is we simply draw a random noise field with the same dimensionality as our target data, and then we build a linear interpolant, linearly interpolating between our noise and the target. And then the nice thing is we can pick any pseudo time step. So pseudo time 0 means pure noise, pseudo time 1 means the target data, and then we can pick any pseudo time step in between and create this linear interpolation. And then the goal is to basically estimate the gradient with respect to pseudo time of this interpolant. And the nice thing is, during training, we know exactly how the interpolant looks like, how the velocity looks like. So we can take the pseudo time derivative, which is here just a constant with respect to pseudo time. So it is here the target data minus the noise. And then we take this noise state and we put it into a neural network, and the neural network should then approximate this velocity as closely as possible. So, but we want to train a forecasting model. So, which means that the neural network will not only take this noise state into account, but also the initial conditions and the external forcing. So the neural network is additionally conditioned on additional data. And then what we simply do during training is we take, for example, the mean squared error between our prediction and the target velocity that is analytically known, and we optimize this over any pseudo time step over many samples, and train a neural network that can basically take any noise state into initial conditions and potential external forcings and predict the velocity for this condition. So we have now trained such a velocity approximation. However, we now want to generate with this model new data. We want to forecast with this model. And so what we actually do is we have our initial conditions when we want to do our forecast. We know them, and then we take noise. We apply our neural network, which is once again conditioned on the initial conditions, and we apply our neural network, let's say 20 times, 40 times, 100 times, until we reached our prediction. And actually, this can be seen as an ordinary differential equation. So this is a generative flow ordinary differential equation. And so we basically integrate the velocity from pseudo time 0 to pseudo time 1. The nice thing about this is that we can change the initial noise, and then for the same initial conditions and the same forcings, we can produce a forecast ensemble. So meaning we can do all the ensemble statistics that we do for data assimilation, that we do in operations. So we can produce an ensemble mean, we can analyze different samples, we can analyze this ensemble spread, and so on and so on. So this is pretty neat. However, there is an issue, because if we compare this to a classical deterministic neural network, which just takes, let's say, the initial conditions and makes a prediction for in 12 hours, we see that we have to apply the neural network n times. So meaning it is actually n-1 times more expensive than a deterministic neural network. So which means that actually this kind of model can be kind of expensive compared to deterministic models and compared to generative CRPS models like operationally used at the ECMWF. So but the nice thing is we can actually exploit prior physical knowledge to make these models more efficient, and we have used this to develop an efficient CS model. So meaning the CS model predicts how the CS develops in the next 12 hours. It takes the current CS state for the Arctic, takes atmospheric forcings, and then predicts actually the tendencies within 12 hours. And these tendencies added to the initial conditions then gives the prediction for the next 12 hours. And we can use these predictions then to do autoregressive steps. So meaning we can feed them once again into the model to go towards longer lead times. And the thing is that here, to make this very efficient, we use a trick which is also kind of often used in numerical modeling, which is domain decomposition. So meaning we split the full Arctic domain at a quite high resolution of around 10 kilometers into smaller subdomains with overlaps between the subdomains, and then we feed the subdomains with the overlaps into a transformer neural network, and this transformer then predicts the velocities for each subdomain independently, and then we stitch the velocities together to basically proceed further into the further in the flow. And so meaning that we do this at each flow step, and so which means that we basically exploit the structure of the flow model itself, and also we exploit the physical localization that we have in the sensitivities for 12-hour prediction. And based on this principle, as I said, we developed the CS model, which predicts all relevant CI states, which takes forcings from the atmosphere, which does predictions in a 12-hour window, which can be extended to autoregressive steps, and which is trained on 20 years of state-of-the-art CI's ocean simulation data. And so the resulting model is quite efficient. It needs below 4 gigabytes of RAM. One can reach around 25 simulated years per real-time day, and actually also a new thing is that physical bounds in the CS prediction are taken into account. So meaning it is taken into account that the CS thickness cannot be negative, that there are many cases without any CIs. This is taken into account. And all this is put into a preprint, which is currently still in review. If we now have such a model, we can then use this model to do rollouts to very, very long lead times. And so what I've done here is I started the simulation in 1995, and then I've run the model for 30 years. And then we can compare this model to the original simulated data from NextSim, so a state-of-the-art CS model, which is copied to an ocean model, compare it to a reanalysis, compare it to satellite observations. And so here I show the CS volume, which is the product of the CS thickness and the CS concentration. And the amazing thing is, this model is just trained to do a 12-hour prediction, but still it can produce the evolution of sea ice in a 30-year window. It can even reproduce the decline of sea ice, and then even the recent hiatus because of internal variability that is also seen in reanalysis products and in satellites. And since this is a generative model, it is also able to basically still resolve all the cracks to circumvent issues with physical inconsistencies, and we can even track the impact of single cyclones into the onto the Arctic sea ice and yeah, see everything with a very, very high detail, even after almost 30 years. And so which means that if we properly train generative flow models, they can actually imitate the physics, how we see it in numerical models. And so now the goal is to combine this with data assimilation. And so the main question for the second part of my talk is how can we combine these powerful generative models with data assimilation? And instead of just showing a single result, I will show a general overview. So meaning I will speak about 3 different parts. So the first part is using these generative models for ensemble generation. Then the second part is about guiding these generative models during the forecasting process itself. And then the third part is a bit related to the AI approach previously, to how we can potentially learn from observations. A warning here: so it is an exploding field. So meaning there are many papers on combining data assimilation and generative flow models. And what I show here is just a small selection, just the papers that I really like. So let's start with first thing. Let's use generative models, pre-trained generative models, to generate an ensemble for data assimilation. And so the general idea is we train a generative model that is unconditioned. So meaning it is a generative model that can basically takes noise, approximates this velocity, and then produces data without any additional conditioning from initial conditions or external forces. And so the general idea is to use such a pre-trained unconditional generative AI model to produce an ensemble, and then to use this ensemble in a 3D VAR system, in an ensemble optimal interpolation system. And so we have done this in a paper in 2024, where we actually used such a generative flow diffusion model. Meaning what we did is we had a deterministic forecast from a physical model, which was here Lorentz 63, so really a toy model. And what we then did is we had our forecast. We then partially diffused this forecast, so we partially added noise to our data, and then we applied our pre-trained neural network to denoise to get basically fields in state space. And then we did this, let's say, 50 times to get an ensemble of 50 members, and then we used these 50 members to in an ensemble Kalman filter. So basically, this is an ensemble optimal interpolation scheme. And so the nice thing about this is we basically learn, or the model itself learns to sample from the attractor, from the invariant measure of the system. And so which means the more noise we add to our deterministic forecast, the larger part we sample from the attractor. So meaning if we just add a bit of noise, we sample a very, very tiny area of the attractor. If we add a lot of noise, we sample a larger part of the attractor. And this actually determines the ensemble spread we get out for the ensemble background. And also it basically determines if we either have Gaussian statistics or non-Gaussian statistics. The nice thing was back then it actually outperformed our well-tuned static B matrix. So meaning it even if we have a B matrix that is full, it was better for even very, very nonlinear cases. However, it lacked compared to a well-tuned ensemble Kalman filter because because the thing is, we don't have any information about the errors of the day, so we don't propagate the ensemble. We just generate the ensemble for the current deterministic forecast. So meaning the ensemble itself is state dependent. So it depends on where the deterministic forecast is on the attractor, but it does not depend on the history. So there's no flow dependency. Okay, so let's speak about the second possibility of how to combine data assimilation and generative models. And so the general idea is here we have this generative process going from noise to data, and we want to guide this process so that we match in the end observations. Once again, we use a pre-trained unconditional generative flow model, so a model that maps from noise to data. And as I said, the goal is that we incorporate observations into the generative score or into the approximated velocity. And so meaning we want to apply our observation operator. We want to compare the observation operator to the real observations, and then impact the approximated velocity. And actually, in the end, the gradient flow going from the prior distribution to the posterior distribution can be similarly seen to a variational data assimilation approach. And so the general idea is we want to, instead of just having, so we have a pre-trained generative flow model which basically provides our background, and we are interested in getting the generative score function of the posterior, and by doing the Bayesian decomposition, we can split this into the prior part and into a likelihood part. And this was recently used by Peter Manshausen from NVIDIA to actually assimilate high resolution observations in the US, and there they compared this to the HRRR system of the American Weather Service, and this method performed pretty well. However, there are also some issues because actually the likelihood itself is the issue, because the thing is, to apply the observation operator, we need clean data, and so here we want the likelihood of the observation given the noise data. So which means if we do the marginalization, we have to project from the noise data to the clean data. And so what is kind of often done, and which is a classical approach in data assimilation, to make a Gaussian assumption, but this can be actually pretty expensive, and the Gaussian assumption might be not valid, especially if we are at high noise levels. Then the projected data might be not Gaussian distributed at all. And an additional thing for data assimilation is that there is the missing cycling between data assimilation windows. There was a recent paper about this. There's also an alternative approach where they basically approximate the score function itself with an ensemble, with a propagated ensemble, the so-called ensemble score filter. But still, it is one of the things that is really missing in the literature. And then the last thing we can do is actually we can combine data assimilation and generative models to learn from observation. So meaning it is really the idea that we initialize somehow our generative model. We use this generative model in our data assimilation to basically produce a reanalysis, and based on this reanalysis, we retrain the model. And with the retrained model, we can once again do a reanalysis and so on. So we can loop for many times. And this is then an expectation maximization-like algorithm. And there are a few papers using such kind of algorithm for generative models to learn generative models from observations, especially. So most of these papers are in computer science, are in computer vision. So meaning they are trying to restore images from noise images, and here we can actually see that so K, so meaning here the first row is the observation, so meaning we only partially observe the image, and then we have the truth here as the last row, and then we increase the number of loops, and we can see that actually the generative model gets better and better, and actually in the end we almost recover what we have seen in the original data, in the uncorrupted data.
Okay, Tobias, you've had 20 minutes, so if you can wrap.
Okay, yeah. So this works for 440 var for model error corrections. This is actually Zima originally used for the IFS, and so it has to be tested if this works better than the AI approach presented by Mikai. But the thing is, it is very expensive. So, and this brings me to the end. So meaning we have now this powerful forecast paradigm. We can do efficient forecasting with generative flows. These generative flows can generalize to climate scales, and we get physically realistic predictions. Then we have promised this by combining this with data assimilation. However, as I said, there's not much done on cycling the data assimilation windows yet. Another question is how to handle an ensemble. And with that, this brings me to the end of my talk. Thank you.
Great. Thank you very much, Tobias. I think we have time for just a very quick question. Let's get it from Martin, Andre. How does the hybrid model solve the problem of the flow model being slow? You still have to solve the entire ODE.
So yes, it is true. So meaning it is still slower than a deterministic model. However, the thing is, so as I said, I use a transformer, and if I would apply the transformer on the high resolution data directly, this would not be possible. And so meaning the domain decomposition is a trick to basically to be able to use or to naively parallelize the processing of the data, and so which means that actually in theory it should more or less linearly scale with the number of GPUs. And so, for example, I have 64 subdomains. So meaning if we would scale to 64 GPUs, we can really scale this up very much like we do in numerical modeling. And so meaning we can really do tricks of numerical modeling in generative flows, and this really speeds up generative flows.
Okay, great. Thank you. Thank you.